Okay, here you go. Immediately somebody shows up. So you find Arthur here. Yeah, so this is Coffee Compiler Club. Anything to do with language implementations and runtimes, typing systems, nullness or not the nullness, or you know, in the case of Cameron and I, we've been going back and forth about threading models and deadlock versus livelock versus throughput and efficiency for high volume, low, short task operations. Garbage collection, I don't know, a million other things are all fair game here. So you're being recorded. This will go live up on Twitter, generally within the hour, a couple hours. If you don't like that, bail out now. Open mic, ask what you want. No set agenda. Cameron and I have been doing something exciting the last week, so maybe that's the good starting point, but then the conversation goes where it goes. I reserve the right to moderate. I never had to do it. That's the end of the spiel, you know, go.
First question, I may have just misheard you in your spiel. I thought I heard you say wide lock, and I later thought maybe you meant live lock. So
yeah, live lock.
Okay,
so
if it was wide lock, I'm going, what's that?
Yeah, exactly. No, I'm not making up words yet. That happens too, but not at the moment. Yeah, so this is, and Cameron can, you know, correct me. So he's busy trying to define a system, which is a set of independently executable domains called services. Threads come in, threads go out. We're calling them fibres. They're not OS threads per se. They're some lightweight version. They are intended to be single-threaded programming model within a service. They can call out to another service and block. The other service takes tasks from all directions or calls in and runs privately on a fiber and then sends results back as they go. So this is a model which says everyone writes single-threaded code as a collection of cooperating services, very similar to like Hor's CSP style kind of thing. And we were talking about what is the set of concurrency notions you want to deal with in this model. And so can I already say that a service runs single fiber at a time, but a service can block. So as soon as a service can block and you call in a cycle, you get a deadlock, or two guys each call from one service call the other, you get a deadlock. Can we prevent that? Can you detect it? Yeah, it's easy to detect. Can you prevent it? Not without doing some other shenanigans. So how about having services that are reentrant? Well, then you lose your safety model unless you demand that reentrant service, for instance, only works on private per thread or per fiber or immutable data or something like that. You have some more rules about when you can say multiple guys can be in there at a time. Can you say have a thread call out to service B from service A, call service B screws around a while and calls back into service A on behalf of the original call into service A? And should that be allowed? This is like the same as Java locks are reentrant, right? But one thread can call the same lock several times in a row, and it's kind of commonly done.
So this reminds me of most of the model behind the real-time object-oriented modeling approach implemented in object times developer and later in rational rows real-time. So the concept there is, you know, was originally called an actor and later called a capsule. So the capsule, you know, as you described, is a entity that kind of services requests. There's no concurrency within a capsule. You know, requests come in and deals with it and sends a reply, you know, whenever it's time. So the unit of, you know, the request is called a message. You can look at it and go, oh, I can't deal with that now, and you defer it. And later, you know, when time is right, you can recall that message and act on it and then carry on. Built into the implementation, though, is the notion you can invoke a message, which requires the receiver to reply immediately. And that's, I've always argued that shouldn't be there because it can lead to the things you talked about, like deadlock and so on. So it was kind of a mess. So I don't know if you've considered those concepts in your search.
So the other piece that I didn't talk about yet was I did this thing called H2O, which is a big clustered computing engine, where the programming model for mathematicians was they wrote single-threaded code, typically over giant arrays, and I auto-parallelized and auto-distributed it for them. But it was commonly the case that during the course of trying to sort some problem on whatever service X, node X, piece X, you needed something from Y, who recursively needed something from Z, and off you go down in the wildebeest of chain of this needs something from that, from that, from that, from that.
Yeah, that sounds familiar.
Exactly, right. So under sort of a similar situation, my system worked really well when the loads were small, as is common during debugging on my desktop. And when the data got larger and larger, we kept hitting various kinds of livelock and deadlocks, and many of which were, eventually we came back and proved that the system would always livelock or deadlock for data sets of sufficiently large size, so that we could put a constant number of threads in, or a constant amount of fibers in, or a constant number of CPU cores in. And under all of these three different things, there was a data set which was sufficiently larger than the set of threads, fibers, or CPUs you had, that you would guarantee deadlock. Or alternatively, we could push it into guaranteed livelock. Some of them would be exponentially long running times, or cubic, because you would be inspecting queues of things not ready all the time, looking for something that was done, as opposed to doing some work and getting it done. So the queue of things not done grew without bound until the size of your data was exhausted, and then you started actually doing real work. And things like this would kept popping up as you hammered the system. So Cameron and I were going back and forth, and I was getting more and more leery that what he was trying to accomplish looked a whole lot like what I ended up doing at H2O. That is, the domain that you're executing in, Cameron, reminds me strongly of the domain that I started out and ended up in when under sufficiently high load. And then I absolutely, and this was a formal theoretical thing that I eventually sorted out, had to have priorities. They weren't user visible priorities, but the general rule was you had to complete somebody else's work before starting a new piece of work. So every piece of work got tagged, it was a new, or it was a continuation of an old. The next piece you had to have was that if you passed the buck off to somebody else, and that passing the buck went around in a cycle, when you completed a cycle, you had to have one to the priority, and exactly and only one. And that would cause you to then handle that cycle ahead of every other thing. And that would prevent the cycle from spiraling endlessly, which was another common scenario where A looked at something and needed something from B, which took a slice off and needed from C, when took a slice and needed from D, and the slice got round and round and round. You spiraled up the ladder of, I need something from some other guy around the cluster. So in my case, it was cluster, in your case, services, but they look very similar to me, until you ran the data set out, or you ran out of threads or nodes or file handles or OS allowed thread counts or anything like that, which sufficiently large data set would run all of these out. So
how are you detecting that cycle in an affordable way?
Yeah, so the thing that we did to force it was to have somebody who was a member of the cycle be present with the message going around, so you could tell when you came back around that you had looped. There's a couple different cheap ways you could go depending on your model. In my case, I typically said you had a CPU, a node in the cluster that was some sort of originator, and you went round and round and you collected them because you might have more than one originator, depending on where the loop actually began. Let me pick up Marco here, Mark Falco, keep saying Marco. But there was some relatively cheap way to detect this thing, that you didn't have to walk the food chain every time you took a blocking call. And then when you, and somehow I would say most of the time we programmatically could detect it. Like there wasn't any work done, except that when you happened to come back around, we knew, like, I want to say not quite at compile time, but the runtime had known before it got there that it was time to raise the priority again. And then, and that the act of raising a priority once per cycle basically prevented the cyclic behaviors from spiraling out of control. So you had to have priority queues, you had to work on things in priority order, you had to raise the priority once per cycle. And you raised it by 1 because otherwise we'd have weird things where you spiraled up too fast and you ate your priorities sort of infinitely quickly. That was another thing that we ran into.
Yeah, it sounded like you would have a count to infinity problem there.
Yeah, exactly. Well, the raise by 1 and then work on the highest priority prevented the go to infinity, but you could still go up really fast. And the easy way to do the priority queues for us, especially since they're mostly low latency and mostly all the queue levels are empty, instead of putting them in one queue and sorting it and doing an insertion sort, we actually had a radix sort. We had an array of priority numbers, and you just went in on the array that you went into. And like I said, nearly always they were all empty because of this. Up until that time, we would routinely have queues that suddenly jumped to millions and hundreds of millions till you ran the array size out, kinds of things. It was, it looked great on your desk. It worked fine. You ran some terabyte sized data set, boom, you blew up in funny spiraling out of control ways. So add 1 around a cycle, work on the highest priority. We had some system-y priorities, which were hardwired to be higher than any user priority, and they were relative within each other as well. There was another major hack going on that I'm trying to remember now.
Seems like you'd also need to get the GC thread pretty high.
Well, we didn't have the GC, we were standard Java process. So you already in the land of Java had this. This is a separate issue with the JVM that I fought with at Azul that eventually made it back to Sun. And that is if your GC threads run at the same priority as your worker threads and your workers are producing garbage, then your concurrent GC thread fights for CPU time. Some early common benchmarks would run many thousands of actively runnable worker threads producing garbage. And the GC threads took an OS time slice of 1 in 1,000, never catched up, and your concurrent GC was not concurrent no more. It just ran out. The same thing happened with the JIT, where the JIT thread took a 1 in 1,000 cut, and your code never got JITted, so it only ever ran interpreted. Right? Yeah. So early benchmark wars were fraught with this kind of stupid things. And to make matters worse here, you can't raise priorities above the default you get under Linux without being root. You can throw away your priority, but you cannot raise it. So if you come in with a process at a particular priority level, all the threads are typically running at max priority, include the user threads. So you had to actually denigrate the user threads, not raise the system threads, because you couldn't raise the system threads without being root, and no one's going to let you run a root in a production environment. So fine. So you had to lower the other guys. And then you ran into the problem that somebody else running on the same box as you. So this is now box-wide priorities. So both within your process, but other processes that are not Java processes were running, they would compete with the GC threads. And so you get a MySQL running on the same box as a Java VM, totally common operation. The MySQL would just hammer the shit out of the threads from time to time. Your GCs would grind to a halt. You take a big ass GC pause on the Java side. And people are bitterly complaining about GC pause as well. There wasn't shit you could do about it unless you lowered the priority of the MySQL, because you couldn't raise it because you had to be root, and you're not going to run MySQL as root. Like, oh, geez, guys, come on. So there was no cooperative way to be polite here, short of having everyone who got launched on the box get their priorities hammered down. So the moral of that story for Cameron is all the priorities start at like the fucking basement level. And then they raise themselves up as they discover they need something from somebody else. The person trying to service the first guy wants to run technically at a higher priority, but the other guy's blocked. So he's running at a higher priority as long as he's running at all. And so you just added 1 when you loop, so you didn't keep picking up new work as opposed to, cleaning out the old stuff.
So I'm guessing too that to the earlier comment, I think that was kind of a small talk thing that Dan was mentioning. But I think the closer analog is probably the process in Erlang. Sorry, not Dan, but Keith. It was probably a closer analog is like a process in Erlang, and that Erlang most Erlang systems were single core, single hardware thread, and but they pretend to be, massively concurrent through the use of these concepts called a process. And a process basically represents a logical queue processor, right? A combination of a queue and a von Neumann machine, right? So I think it's probably closer to the model that we're using.
Do you have a mailbox for each of your processes?
Conceptually, most
That's
of
all
the
it
time,
takes.
most of the time, most of the time, invocations against a service are actually inlined. So you just jump from your service, you subsume ownership of the service you're calling. And until it's a contended service, that never changes.
Yeah, let me.
So if I have a pattern that I'm going to send you a lot of work and occasionally I cancel it, is there a way for me to be like, hey, I don't want my cancel message to be behind 1,000 work messages?
Nope.
The same for H2O, by the way. We kind of managed to hardwire some in at a different point, because the usual workload was, here's a vast array of data. Okay, fork it in half, and now you have 2 half vast arrays, and you fork and fork and fork. And then you had a roll-up tree and a fork out. And if the cancel came along, you had to crawl up the tree as fast as you could, telling people, stop it, stop it, stop it, stop it. And the usual cancel was because you threw an exception because you had an error in your code. But everyone's running identically same code. So you got 100 million exceptions coming back at you, right?
I mean, the same exception
prioritized-
coming back at you.
Same exception 100 million times. That's right.
But there is a prioritized queue concept. It's just not, surfaced. So because the system conceptually, again, like I said, this queue may not even exist. This mailbox, as you call it, may not even exist. But since the system also has to communicate things, kind of a control plane, I think is what I called it, Cliff. So for example, if I have a service A and it calls a service B, when that call occurs, conceptually, service A creates a future for the call. And then service B, when it completes the call, places the result in the future. Okay, so that placing of the result isn't a mutating operation by service B. It's actually a message to service A saying, I've completed. Now, again, this is conceptual. None of this actually ever happens except in highly contended situations when we spin up all
my warning for you, Cameron, is if you are not monotonically degrading under load sort of smoothly, then you have a control theory problem where under high load, you will be highly unstable on your performance, and you'll go into the contended state where you will suck big balls and be horrific, and the contention will remain until you completely wipe the load out, and then you'll spring back to your efficient model. That you must have I want to say, standard control theory thinking in place for how the fall down paths go, or else you run into this highly unstable mode where performance is on or off according to load. Am I making sense here?
Isn't that always the case when your load is heavier than you can process it?
No. Suppose your load's heavier than you can execute, but you can contain the load. You can hold the concept that the load is there. So I hand you a terabyte array of data to go do work on, but that's in a little tiny object that says for 1 terabyte, takes no space. And I split it in half, and I'll have 2 half terabytes to do, and then 4 quarter terabytes and whatever. So I have lots of these little things, and the issue there is that the concept of holding the load isn't too big. The load itself is much bigger. So what you don't want to have happen is the act of doing too much load causes your concept of holding the load to scale without bounds, and that become itself the load. Like you have some overhead for dealing with having the load, but you need to have it monotonically increasing as you monotonically have pending load, and never get into an n squared or worse. Because I have pending load, I have more work to go do to deal with pending load, not actually doing any load. And that was a key performance thing, that if you failed that test, then as your pending load grew, the amount of time you spent working on load versus pending load fell off until you spent all your time working on pending load and none working on load. And that was the fall down case. Now the load comes in as a continuous stream, like someone's feeding you load, you can spike really big holding pending load. And then if the load ceases and comes off, you can peel it down and then you go. And your throughput of work, not pending work, but work over time is the same or very close to the same. You lost a little fraction to handle the extra pending load dealing. But you never want to be in the case where the concept of holding on to pending load grows without bound. That is the effort to hold it grows without bound, because that dwarfs getting work done and then your system's unstable.
So I think all of that comes into the idea of ecstasy services having a scheduler behind them, which right now it's just FIFO. And Cam, I'm not sure if that's intended to stay there permanently.
Right. What I'm saying for what I experienced at H2O is I absolutely had to go from FIFO, which is what I first did, to priorities. And furthermore, the priorities had to have this funny game where you counted cycles. And otherwise, as pending load came in, you accidentally made more pending load instead of cleaning out the load that you had. So like I could keep a terabyte in a little tiny thing, but if I broke it out into the smallest chunk I'm willing to have a guy work on, I would have 1 million of these chunks. And suddenly my effort of holding the 1 million chunks is 1 million times greater than holding on to one. So I didn't want to break the one into two until I first cleaned out other things.
So that's what, before this redesign, that's what we called the prioritized reentrancy. And that was the default for services. So prioritized. Does that make sense?
I wanted to ask. I wanted to ask
priorities to any user because they couldn't figure it out. That was all.
How is this different than like Kafka with its big giant circular queue that could be potentially replicated on multiple cores for reproduction
yes.
versus priority that you're talking about?
Yes. So Kafka is a message passing bus. It holds on to pending work, which is very similar to what we're talking about here, except that we have unrelated nodes. I call them nodes, Pam calls them services. In this concept of this domain, they're pretty close, where each one holds its own queue, and they're unaware of what the other guys are doing. And so you want to have a theory in place that says, I do what I do, and whatever I do, I don't cause somebody else to go bad. Because the usual rule is I do something which causes this guy to do something, and then that guy, and you circle, and you come back around to yourself. Then you have a self-induced feedback that you're not aware of that is going around in a cycle, and you burn yourself out that way.
I saw this problem at work once with the disaster recovery test, where we had 3 systems that got taken down by a chaos monkey. And then when it came back up, none of them were doing any work.
Because they were all fighting to get
doing the investigation to figure out what happened.
Yeah.
And it turns out that there was a system that had been deprecated 9 months earlier. And each of these 3 systems were each only processing the output from the other system. And none of them were doing any useful work. And all 3 should have been deprecated, but we failed to detect the cycle.
There you go. Yeah, that was, I mean, I ran into cycle deaths after cycle death after cycle death at H2O that were all possible paths, bizarre things you never thought of that would lead into, the death spiral. I ran out of OS threads, so I refused to spawn another one, and in which case that particular job didn't make forward progress. And so I did other work, and suddenly everyone was deadlocked waiting for somebody else because we all ran out of OS threads. We all ran out of work fibres from Doug Lee fork join. We all ran out of, and we could get them all run out of CPUs too, just plain old CPUs. So it was just, until I got the theory right, under sufficient load, it got wedged every time.
So how do you decide what order to do working? So let's say I have some big tree and I want to know what is the sum of all of the nodes in my tree?
Yeah.
So clearly depth first is wrong because I'm not going to get any parallelism out of that. And breadth first is wrong because I'm going to get so much parallelism, I'm going to choke my whole system.
So I did this with the Doug Lee fork join and his theory. And so this is, I totally agree with it. I'm just copying from Doug Lee, so giving credit here. You take your big thing and you split it in half. Then you leave half off to the side and you take one of the halves and you split it. And then you take that half and set it and split it and split it and split it. And so what happens is you tend to get powers of 2 of work available sitting on work queues. And people steal work, and people, grab from each other, and people, occasionally we would have systems where we actually wanted people to double compute because we needed the last tail to disappear or whatever. But the typical statistical process was everyone was working near the leaves. There was always a power of 2 more work available by simply grabbing from somebody else, and you got some power of 2 big old ass hunk of work. So it was, in practice, was very efficient. The amount of pending work was logarithmically capped by this power of 2 thing. Statistically, we didn't have to actually do anything to make it stay that way. It just happened to be that way because you always grab from the tail of the queue, which is always the smaller chunk of the pending piece and shit like that.
What makes the tail always the leaves?
I'll get this backwards. You grab from the fat end. You're correct. You grab from the fat end, and you grab from not the leaves, because the leaves are being actively used. And the grabbing logic had a rule that said, if I'm far enough away from the leaf, then I can steal without atomically interrupting the other guy.
The worker threads in the fork join pool pull from one end and insert into the other. And when you steal somebody else's work, you grab from the head or whatever. It's just you work on opposite sides. Right. So I'm curious, Cliff, with your in H2O, with using the fork join pool, I presume you had many active usages of the same pool at the same time, trying to solve different problems? Because that's the thing I've always seen that appeared to be wrong with the fork join pool is you can't effectively share it. It becomes very FIFO-like when you share it. So it's good to solve one massive problem at once, but you have an alternate experience.
We ran everything through the same pool. So we had one pool per node.
Non-FIFO-like behavior?
Well, right, and plus the priorities. So the priorities broke out your FIFO behaviors.
Okay, the fork join pool doesn't have priorities, but you were able to.
We forced priorities onto the fork join pool. That's what I'm saying. I did it with thread priorities.
But was H2O usually solving one big problem, or was it, I've got 7 different analysts who are each throwing problems at me that are unrelated?
Equivalent. One analyst said, run a hyperparameter search using the following things. Oh, I have 17 different models I'm trying to build, each with their own pile of hyperparameters. It just looked the same as 17 different analysts coming in. You couldn't tell the difference.
But what I've seen is, like, let's say I throw a problem at the fork join pool that's going to take it, 10 minutes to answer.
Yeah.
And it starts churning on that. And then I throw in 5 more that are going to take, 10 seconds to answer. Those 10-second ones are going to be queued up behind the 10-minute one. Like it doesn't. Right. But I see you may have solved that with prioritization somehow.
Right. So we did priorities for the OS for things that were going to be quickly GUI displayed. So we didn't come through and make an estimate of the size and the time. Like if you threw a thing in that takes 10 minutes and you threw a thing that takes in 10 seconds and you threw a thing that takes 10 hours in, can I tell ahead of time the 10 hour from the 10 second from the 10 minute? No, not unless you tell me somehow magically. Sometimes you could tell based on data set sizes and whatever, but you're totally throwing a heuristic in. So because you can't tell, there's nothing you can use to make decisions except pick something. These are all in the same priority and pick round robin between them.
So I'm pretty sure I've talked before on this call. I've been working on a fair scheduler in Java that kind of mimics the Linux fair scheduler for years. And kind of the latest thing I've been doing with it is making a lightweight fork join pool, which ends up, it appears like it solves this problem, right? You get all the threads in the fork join pool churning on some multi-hour problem, and then you start throwing smaller work at it, and the fairness algorithm starts to say, oh, no, these other things which haven't used much CPU, we should give them a crack at it. And they make it to the front, get out of the way, finish, and then we go back to working on the long-term thing. And as like evaluating the fork join pool, I was trying to like understand like what is its key flaw, and that's what I kept going back to. It's really good for solving one big problem at once, and any other thing, even if you create multiple fork join pools on the same machine, it's not geared for sharing. It's geared for one big scientific problem.
Your perspective seems to depend on your notion of what constitutes fairness. The guy that arrived an hour before you doesn't necessarily get precedence over you.
Yeah, I could say it differently about making the end users happy. Like the guy that was it was gonna take an hour for his job to complete. If it takes an hour and 10 minutes, he's probably not gonna be that ticked off. But the guy that was gonna send in a 5-second job, he's definitely gonna be ticked off to wait an hour for that to go through.
So the one thing I've seen that smells like that is I've seen systems that have different queues for how much work has already been done. So you're high priority for the first 100 milliseconds of work, and then you're a lower priority for the rest of the second, and then you're a lower priority for the rest of the minute. And once you've been working for a minute, it's like, oh, you're a totally non-responsive thing. You go in the big queue with the rabble that take a long time to finish.
I want to say we did something to help short jobs come through independent of doing GUI. GUI things got a higher priority. We kicked up things that we knew, but we knew by fiat, by the designer, that we would say this was a GUI priority. It wasn't that. And I know we did something that it turned out to be okay, but we didn't do anything explicit. Like your timing game sounds like the right thing to do.
Yeah, I've even seen that with things like JITs. That's like, no, you get no jitting for the first 100 milliseconds, because if you're going to be done in 100 milliseconds, I don't care.
You don't care. Yeah. Well, you want to profile some too. But yeah, the general prediction is if you've run time X already, you'll probably run X again, at least, with an exponential decay on you. Yep.
Yeah, people are definitely way more sensitive to, I want my 100 millisecond thing to take 100 milliseconds.
Oh, everyone has
and if my 10-minute thing takes 10 minutes and 100 milliseconds.
You don't care, right? Yeah, yeah. There's an expectation, and then there's a ratio of runtimes that minimize the ratio of with and without load runtimes. But we definitely worked with multiple analysts piling in on the same box. It was all fine. It was common that one guy would start because he was the champion in the company and doing something, but then somebody else would pile in if they were getting active, and then they'd sit down side by side and talk back and forth and start kicking things in, doing whatever they were doing. And so we would see that as well.
Do you ever find you had problems with defending the scheduler?
What do you mean by defending the scheduler?
So I had a grad lab that was learn how to do high performance computing things.
Yeah, right.
And you could almost never schedule everything because there was someone running a super computationally expensive job on the Bastion host that you were supposed to use to schedule the cluster.
Oh, on the no, the system was peer-to-peer. You could schedule from any node. So the OS had to give your Java thread running the GUI response. It was typically a web-based interaction. And you had some command line things that did a web interface under the hood. But the entry point in the cluster was basically an HTTP hook. And that ran at very high priority, not as high as some of the system and no deadlock need things, but pretty damn high priority. And introduced fork under the fork join pool and then went back. So you didn't have to defend it in that sense. A more common scenario was someone would put the H2O node next to a MySQL cluster. And it would run a database job to get the data and then do machine learning on the data. And the database was also doing other shit. And then, you had heavily unbalanced CPU loads you didn't plan on. So you thought this would take you're forking off tasks of certain size and shape. And eventually you get stuck waiting. Everyone's waiting for something to get done from some last slob at every junction point where multiple people waiting. There's always a last man in. And sometimes the last man in was stuck waiting for my squeal to get done, and nothing you do about it. It is just what it was. Yeah, there were a lot of last man in optimizations. We did a lot of performance profiling where we looked at the forking out and the gather and kept the times spent of the long path through the gather. Like if I fork, so I look at some point and I have some single thread till a fork time, then I forked, and then when I joined, I grabbed the longer of those. So the last man in was the longer, and you took the delta between. I ran these two in parallel, but this guy was short, so I had some slop. I hit the long guy, and then I had a tail. And then I had a cascading tree of these going like the fork here. This guy did the same thing in his join. So you gathered globally the long path through. And then if you ask for the profile data, you could routinely or cheaply tell people what the long path was. And then you could go look and see if there was something going on that was not obvious. Like you had a bad distribution of the data so that somebody had more work than anybody else. And occasionally you had the bad distribution where the loser all got stacked in the same direction for whatever reason. So the same guy ended up doing all the big pieces all at once. And that was
Similar to getting a big chunk of work. Did you do anything to deal with like a spontaneously slow node? I've seen clusters with 2,000 nodes in it, and the fastest node is 10% faster than the average, and the 99% is 10% slower than the average.
Yeah.
And then there's like 3 nodes that are 1,000 times slower.
Yeah, right. And no, we thought about it. We went round and round on this. It was more effort. The trick was you just wanted to do what Google would call the curse of the last reducer. You just wanted to redo the last piece of work on a different node. And those guys will come back later, much later with some work. And you're like, we did it already. You don't care. You know, shut up, go away. And we started down that path for a handful of things. Like some of the system internals would do that very job. Like I knew I could do it here. I knew I could do it there. I started it here. If it didn't come back soon, I started it there, and I started it there. And eventually somebody came back and did it. And then I had to be prepared to handle receipt from these other guys. Say, we did it too. And you'd be like, I don't care, but you had to handle receipt of that. So it was not a thing that we set up by default. We knew it
goes back to the there is no work cancellation in H2O.
Well, there was work cancellation, but there was no way to hard guarantee it rapidly. You pushed it forward. It was always a higher priority message than the work you were defeating. So it got executed first, but it went on the fork join queues the same way as other people, just at a higher priority. So it pulled off first, but somebody was already doing work. And while they're already doing work, they're in a job position of forking more work. So there were definitely some anti-patterns that we fell over that were like, I'm in a single thread going to spawn work in a tight loop. And I pile up a bunch of pending work. And that gets to my conversation I had with Cameron earlier. You don't want to have a thing which endlessly spawns pending work. You want to say, if you fork in half, and then you work with the half, and you'll eventually fork the other half, you kept your pending work, the half of the pending work is kept as one thing. If one guy spun off 1 million things on a tight loop, you couldn't cancel them. And then you had 1 million things on your queues you had to unwind.
It almost makes me want to use the same trick for you're taking a long time to execute, to be like, dude, you spawned 16 things. I'm dropping your priority because you seem to be a high spawner.
Yeah. I like I did so much work already. But so here's another piece about that. I did so much work already. What did you mean by who is the unit of this much work? Everyone's forking parallel work constantly. So I just did a chunk of work. Okay, I'm about to join into some other chunk of work, and we can accumulate. And at some point we've come back around to what? Some half that got forked. Here's the other half, his left half, which the right half knows nothing about what the left half is doing, and vice versa. The right half's still in the queue. The left half took an hour. I would like to tell the right half, your left half took an hour. You need to be low priority, right? And so it's like, you're tracking all those around. It's doable, kind of a issue. And normally I'd say the left half's done. I go back to my future and I'm waiting. And of course the thread gives up and goes and does other things, but the futures sit there with half done. Instead, you'd say, go find the other piece of work and tell him his left half was big. Well, the other piece of work got split and split and split and split, and they're all the way down to leaves. And now you're chasing after him, going with, hey, you should be low priority if you're trying to catch him, right? And he's like, I'm splitting and working and splitting and working, making progress. Maybe you catch him, maybe you don't. So we didn't go there, but I hear you. We had people talk about it. It was all these concepts, it's like Cameron and I and Cameron's crew is a bunch of people on the list. We're talking about all this stuff. You could do this, and you could do this, and you could do this. Wow. Talking about it's way easier than doing it.
I mean, clearly you want to prioritize that list by customer pain, but
yeah, right. And so the first thing was,
we were starting from a much different point, though. We were starting from a situation where we had data corruption because of unexpected concurrency.
Yeah.
So that was a far different problem than scheduling. That was just a fundamental logical.
So
that counts as customer pain.
We had data corruption as well due to unintended concurrency, and that was like a different thing to be solved.
I don't think we've really tried to tackle the scheduling problem yet.
Right, that's what I'm hearing.
It was all about oops, there's corruption. Let's focus on that. And for now, FIFO scheduling is sufficient.
That was what was triggering in my memory. Your conversation with me about how you were dealing with concurrency struck me as, I've been there. I suffered to that. That doesn't work well. And it took me a while to bring up the nomenclature you're using to the memories of H2O of going through this transitional period of having load and then having more load and more, and all the concurrency bugs that came out of that, which ultimately were a lot worse than the concurrency bugs that deal with corruption.
So we've basically never had concurrency bugs until this. That's why this was such a big deal, because we thought we had a model that would naturally prevent them. And then to realize that we were struggling with the same
I heard it.
conceptual class of issues that you would deal with if you were dealing with
Java
threads, for example.
threads just doing their shit. Yeah, I heard you. I heard your pain.
So maybe Mark, maybe explain the concept that we came up with for
concurrency
preventing it.
safety.
Yeah.
Yeah. So yeah, we talked about it a little bit last week on the call, but to kind of, well, yeah, both go over that and catch everybody up. So the basic idea in Ecstasy, you have all these different services, and those are your units of parallelism, and each service holds its own mutable state, and that mutable state can't be seen by any other service. And each service has a number of fibers, but only one of them can run at once, right? And so the idea is, well, like no one else can see your mutable state, no other thread could see your mutable state, so there can't be corruption. And fibers are single threaded, right? Like all fibers for a service effectively run on one thread. But we could get into reentrancy issues, right? Where service A calls service B calls back to service A, and we let that re-enter the service, and it went through and touched the same data structure, and like, oops, now we have corruption when you get back to the original fiber. So the model that we're looking at now, so the old model was kind of a little bit like Java in terms of how you declare thread safety, which is, I would say you had to opt out of thread safety, and that you said you effectively said, yeah, this bit of code is not thread safe, right? We didn't use the term synchronized, but that was, think of it like Java. You say, yeah, I synchronize this because I'm not thread safe. And now we've flipped it and said, no, you have to opt in to being run concurrently, right? So if you don't say that your code is concurrent with an at concurrent marker, you're assumed to not be thread safe, and we cannot let two fibers from the same service ever be in that code.
So
and so the way that
it's just a stack of execution frames, right?
Right. Yeah. Lightweight
way.
threads, whatever you want to.
A fiber is a lightweight thread. Right?
Yeah. So now you could say, like, we have you start writing your service, and as the author of the service, you want high throughput. So you're probably writing concurrent code. Sorry, my dog is not on my lap. She'll be barking or whining. So you start writing your concurrent code, right? And then at some point, as an author of a service, you're using somebody else's code, and you call out into something that's not thread safe. So maybe some hash map implementation hasn't been marked as at concurrent. In there, if that thing tries to call out to another service, either because it's directly calling out or you pass in some lambda, the fact that you've gone from concurrent safe to unsafe, once you've had that transition on an individual fiber stack, you cannot re-enter. Well, that was the initial idea, is you can't re-enter the service, right? And the unsafe code, we mark that with at synchronized, but unlike Java where you're synchronized on the object, here you're effectively synchronized on the entire service. So at no point can you have two fibers in a service both inside synchronized code. Like that just can't happen. So if you call out from synchronized code and it tries to re-enter, like, well, that's not allowed. But then we opened up the doors a little bit more and said, well, it is allowed, but it's only allowed to call other concurrent code because that code was said to be concurrent, right? It is concurrent safe. So the bottom of fiber 1 stack is concurrent and the top is synchronized. Fiber 2 comes around, it can start moving to the concurrent code, no problem there. But as soon as it hits some at synchronized code, it's like, no, can't go in anymore. So now it blocks, which allows other fibers to potentially go through concurrent stacks, but no two fibers could ever cross into the synchronized code.
So if a developer lies to you, have they shot themselves in the foot? Have they shot the whole system in the foot?
They've shot themselves in the foot, right? I mean, if you say your code is thread safe and it's not thread safe, like, yeah, I mean, you're in trouble. But versus the current traditional model, which is like, I didn't say anything, and the runtime says, yeah, you're probably thread safe. Like that seems crazy in retrospect. Right?
So if I'm writing malware in Ecstasy, that's where I should start.
Yeah, but you're going to hurt yourself. Like ecstasy is everything's container. So yeah, you'll hurt your container, right? But the other things running inside the same process space, they're fine.
Well, then what happens is you hand corrupted data back out of your service because you took corruption, and the guy that was blocking waiting for a reply from your corrupted service gets corrupted reply.
Yeah, I mean, bad code is bad code, right? Like,
Yeah, right. Yeah.
Yeah, I can write code that, like, I call put on my hash map, and it's like, you mean clear, right?
Yeah, right. Yeah,
memory.
the Elm thing, Elm has this deal where if you call away from Elm into JavaScript, when you get a result back, it must be strongly type checked on the spot because you don't trust what you get back. And then
Nor should you.
yeah, exactly, especially in JavaScript. And so they called it a port, and you go out of port and you come back in a port, and when you come back in, it's all strongly type checked. You say
So
it's this, let
ecstasies-
me verify.
Yeah,
Ecstasy
Thank you
Java
for coming in,
generic said that.
JavaScript. Well, thank you
One
for
at a
coming in,
time, one at a
JavaScript
time.
object. Please go to customs to be checked.
Yeah, right. And there's
So
some
actually-
overhead there.
Ecstasy
It's nice that
actually
they did
doesn't-
that for. Oh, sorry, Cam. Go ahead.
I was gonna say, if I try to return from a container, if I try to return something from a request that came from outside the container, I actually don't return, I'll put it in quotes, a value. I return a proxy to the value, because any attempt to invoke anything, whether you're just getting a property on it or calling foo, whatever, any touching of that thing that's being returned from the container has to be touched inside the container.
Dinner or not dinner?
Right. And then there are obviously optimizations for handling things like, if I have a shared type system between the two of them, I can copy the data up. So like if it's an array of int, sure, I know how to copy that safely, right? But any other object that tries to get returned from a nested container comes back as a proxy instead, comes back as a service proxy. So
And if
that
the
way,
parent doesn't have the type, what happens?
that's fine. That's perfectly fine.
Well,
Like,
there has to be
the parent has the interface type, because
yeah, interface
otherwise,
type, yeah.
right, has the interface type, but it doesn't care about the class type. The other thing is if it's a nested container, the container above it can do whatever it wants with the container below it. So whatever the container is above you is God. Like, that's the,
Right.
you can't see up, but whoever's above you can see down. So, but anyway, so
Yeah,
we
I'm curious
don't
to
just
see how
encapsulate.
well your system works sort of more in practice and more under load and all that.
Oh yeah, so are we. I mean, we just finished our first database stress test 2 weeks ago. So like, we're still pretty early. That's a database built in Ecstasy. So
Right.
stress
Yeah.
stress testing in Ecstasy. So
It's not SQL, right? So it would be hard to run like Jepson on it.
it's not SQL. So
There you go.
as a former DBA, SQL is not high on my list.
I did a bunch of work for a company building a new alternative database language to a database, and they had to know how well they would do on TCBH queries. And the answer was, sucked pretty bad.
This is the Julia one, right?
Yeah, it's the Julia one.
But
Oh, they suck.
trust me, right now we suck worse. So
Okay, they're
Yeah.
pretty bad, but maybe you could.
Porting someone else's benchmark to your language is often, we
yeah.
got a huge speed up. What'd you do? We changed the code in our porting of the benchmark.
Yeah, no.
Okay.
No, their implementation has issues to do with runtime, low-level data structure representation and low-level runtime thinking, and no concurrency. I think Cameron's probably got overheads that are different, and I question whether maybe if you're a million times slower on the left and a million times slower on the right, plus or minus 1,000, who cares? It's pretty bad either way.
well, we're currently really slow because everything is interpreted, and the language is explicitly not designed for interpretation.
Yeah.
So basically, the compiled form of the language, it's not a low-level IR. It's a very high-level IR. In fact, you can almost perfectly decompile the IR to the language.
Yeah.
If that gives you some idea. So for example, if I have a line that says, if I equals 0, and then the next line says plus plus I, the bytecode will literally have in between the instructions for those two, there will be something that says, advance 2 lines, right? Like there's actually an op for jump forward 2 lines, right? And that's because, Java sideloaded all that in the IR to these tables. So if you look at the Java class structure design,
Yeah.
there are all these ancillary tables, like we'll throw that exception table over there, the local variable table over there, and it's a bitch to work with, unless you're writing an interpreter, in which case it's better. But like our goal was never to have an interpreter. Our goal was to have kind of a perfect IR that represented what the language got, type checked as, so that the job of the runtime is to lower the IR probably from our IR to an LLVM IR, for example. So we're really slow, but designed to be really fast, just temporarily really slow.
Every story everywhere, but I'm going to be there at some point, so I can't say much about it.
It does seem like a lot of people are using LLVM these days.
Yeah.
I wonder what percentage of all register allocation that happens on computers is done by LLVM, GCC, and JVM.
Yeah,
I feel like it's doing most of the register allocation in the world.
No, I suspect it's V8 and friends in the browser. And then the hotspot by a huge margin, because it runs every time you do anything. You kick off a JVM, you get 10,000 compiles. Everyone's got a serious register allocator in it, right? And so, I think that the hand roll LLVM, when I do a make, that is never ever going to touch the automatic kickoff of the compiler in a JVM.
Well, what about Azul, Artur? Plugging in LLVM.
Yeah, we're working on it. We're increasing the number of LLVM compiles in the world.
You might get there. So I'm saying he's there's a thing there. you got a problem that you're not as widespread as Oracle hotspot, so that makes it difficult to.
I've been running the Azul VM.
There you go. That's 2. Wait, are you running the one with LLVM backing, or just the build of the old JDK?
I think I'm running their Mac JDK, their native Mac JDK for the M1.
And is that LLVM based?
No, it's OpenJDK.
Yeah, OpenJDK. Right. I'm running an Azul OpenJDK build. Yeah. I bumped to Java 15 stupidly from 8 finally after many years, because I wanted large text strings in code.
I was curious, did MLIR meet its hopeful criterion from Chris Latner to sort of introduce a LLVM common superset so that each language does not have to rewrite basically everything in LLVM?
You asking me or someone else?
I don't know. I'm reading up MLIR right now.
So
well, I can
as I look at this, okay, go ahead.
Yeah, I can answer for us. So we're obviously doing Java in LLVM, and we started it before MLIR came to life. So we have to express various high-level concepts in LLVM IR, and we go long ways in order to do this and in order to optimize these high-level concepts. If we had an MLIR available at the moment, yeah, that would have been a convenient way to express this kind of high-level semantic and then lower it to LLVM. But we do it without MLIR.
So I'm surprised Matt hasn't said anything.
Yeah, I'm just curious if it's like a lack of sample code, a lack of maturity, that nobody talks about MLIR, but that is Chris Latner's next LLVM. So it's a little bit conspicuous now. We don't hear more.
I think it's a pretty early technology at this point, and just as Artur said, a lot of languages that needed to do that have done it already. So Rust has its own intermediate representation. Swift has its own intermediate representation, and it would be quite an engineering effort to rewrite all of this from the scratch to use MLIR. Although there are some machine learning compilers that are currently using MLIR, as well as hardware synthesis compilers. So really tools to replace Verilog or VHDL like circuits, which are, I think, quite interesting. But that's relatively new. It's not traditional programming language implementation.
All right, go read the talks and related works to see a bunch of stuff with TensorFlow.
Yeah, I think that was the initial motivation for introducing this this representation and this framework.
High performance
were
GPU
originally-
tensor code
The-
generation.
The core of MLIR is still LLVM, but the reproduction of your runtime, your libc, et cetera, can be less laborious, according to what I read a year ago, maybe.
So the code generation issues I saw from Julia were related to LLVM not understanding it was in a JITting scenario, not having profile data, not understanding it was in a JITting scenario, and therefore it was lazily cross-calling to other LLVM pieces. The lazy cross calls were done in a very inefficient way. So if you were within a compilation unit, you looked pretty good, and as you cross compilation unit boundaries, you look pretty bad.
Yeah, LLVM was built, I guess you could exaggerate and say it was built to help replace the back end of Clang, right? Like,
Yeah, right. It's a static backend compiler. I get it.
Well, and MLIR wouldn't help here. So where it would help is if you have some high-level constructs you want to optimize on, like, I don't know, subtype checks in Java, virtual calls, things like that. It's just a convenient way to express these high-level things. And what they use it for various machine learning is they have various matrix operations, which they optimize on that level of abstraction. After that, they lower to LLVM and they do low-level optimization. It's just much easier to do high-level.
So when you initially were working with LLVM and there was no MLIR, were you literally having to write your libraries in the LLVM IR?
So I have a talk on that. I made it like 4 years ago.
Throw a
What
link in.
we did, yeah, I'll send a link in a
Good
moment.
idea.
So essentially what we do is we have a like set of functions we call abstractions. These are functions for various VM operations. Let's say resolve a virtual call, resolve indirect call, do a subtype check. And then in the optimizer knows of the semantics of these calls, and it can optimize knowing what these functions are doing. And then we inline these functions. So we start with these kind of calls where we have calls to resolve indirect call or whatever, and then we inline them gradually. And these inlines are essentially lowerings of IR to more low-level representation.
I did some things like that in C2, where there was always a default path that was pretty generic, and then immediately you inline. But I didn't have it specifically called an inline. I just did a substitution for a lower level concept.
By the way, there is one language in progress that is actually going to use MLIR, and that's the Flang Fortran compiler, although that's still work in progress. And of course, they have their own dialect. So really, one point to make is that MLIR is not really an intermediate representation. MLIR is a framework to create your own intermediate representation. Those intermediate representations, the right tool for the right job, you have so-called dialects. For example, the affine dialect corresponds to the polyhedral optimizations of for loops. And Flang has its own IR, it's called FIR, that can represent some of the higher level concepts in the Fortran programming language. So that's, I think, one example that is a work in progress right now.
It feels like we're a lot of years into this to still be arguing, wait, how should we represent a program?
You know, I came up with the right way to do it, and no one listened to me. So, you know, that's just our problem here.
Ah, problem solved then.
What are you talking about? A lot of people use stuff here. No, the thing is, Aaron, that, you know, that there's a juncture between what you're producing, what you're spitting out on behalf of the source code that you're being fed, but it also has to interface, some FFI, whether it's only known by the compiler or not. I mean, it has to interface with a pretty big stack of functionality that's been pre-written, right? So it used to be in the old days, we would write the runtime library in assembly 100%, and then the compilers would link to that, and you'd have I'd have the addresses on a piece of paper next to the computer. So it's like, okay, I need which one, fixed address. So
No, I think there's a different question or different comment from Aaron. There was or maybe from you, Cameron, is the IR and the language it's supporting I won't say go hand in hand, but they like dog owners and dogs, they tend to look alike. They're
Yes.
obviously different, but they tend to look alike.
Yeah, there's exactly one language that you can implement using the Java IR, and it's called Java. And anything else,
Well, people try.
Yeah, there's plenty of other languages that are trying, and some of them do a good job. So I claim that that's not entirely fair. They do a good job. Closure and Scheme are two of the big languages that have done a good job.
Okay.
But it's not that convenient.
And it's not that convenient. And there are things they would have liked to have done differently had they had a different low-level primitive they could have built on. And then they give up.
Right.
There's no big integers by default baked into the language. And that's because you would have to have serious IR support to do it efficiently. So big integers, a standalone thing, and you ask for it when you need it. And if you don't ask for it, you don't get it.
And with languages like Closure, even their concepts of looping are different because they didn't have tail recursion. And they were like, I would have liked to use tail recursion, but no.
I thought maybe not. Maybe it's
Scala added a tail recursion optimization, but it's a little bit.
Put it at the high level. Yeah. Okay, fine. Yeah. Yeah, I'm wedging tail call optimization, whatever, tail call elimination in my IR directly in AA, because it's a bitch to add afterwards.
So what do you mean you're adding it in the IR? Explain that.
Calls are actually broken into a call and a return is a jump to a continuation. So a call squirrels away a continuation in the IR, and a return takes a continuation and jumps to it. That's the semantics. It's obviously nodes in a node graph, but that's the semantics. The continuation itself is a first-class citizen and can be passed about. Now, I'm not doing anything with it right now, so all my calls all return, but the hooks are there to say I can tee off and go somewhere else with this continuation, come back. And in particular, I can say, instead of jumping to the go back point, I can look at the go back and say that's another go back and just start, winding up the multi-returns. It's tail call, winding up the tail call eliminations in the IR as part of the normal activity. Like the C2 at some.
But you're doing that folding at call time, not at return time, right?
Yeah, but at the time I generate the IR, I have both halves right in front of me. So they're linked together in that state, but then you have to put some dependency edges floating around to track which one is which and who's returning to what from where. And at the time that you see that you've got a call followed by a return, the calls were already broken for me into a call prologue and a call epilogue. And a call epilogue followed by a return are two nodes of the graph that can be squished. And that's the tail call elimination, because I broke the call and it's not a single node in the IR, it's two now. There's a prologue and an epilogue. And the value for what the squish is and where you go to is a continuation. I'm calling it a return program counter RPC, as in the old x86 things. And I track them directly in the IR everywhere. And so if I do tail call elimination, I'll still be able to tell you who's returning to what, even if it's an indirect or shortcutted return or whatever, because I'll know I have the list of RPCs.
So if in the IR I have a call that is not followed by a receive return, then it's not possible to return from the function I just called?
I'm sorry, no. If I have a call, I'm sorry, say that again then. I missed then.
If I have a call, normally the next instruction is going to be a receive return.
Oh, I see what you're saying.
If I don't have that receive return object as the thing after my call, does that mean that there is no return type and this thing can't be returned from?
So right now, when I generate the IR, I generate the call prologue and the call epilogue back to back, and they're linked. If I decide I want to go to a tail call eliminated version where the call epilogue and the return are collapsed, there'll be something else after there. But yeah, you're not returning. That's the whole point. You're returning to some upward stack piece.
So what happens if I have a call prologue but no call epilogue
That's what I'm
immediately
saying.
following it?
You're not returning. And that is exactly what you asked for. A call
But isn't
prologue
the-
with no return is a jump to somewhere else and carry along the hook saying which way I'm going to go to. But it's a jump. And a call is a jump anyhow at the hardware level. It's a jump and put the hook somewhere on my stack or somewhere in a register or whatever. So
Yeah, it's probably going to boil down to, instead of saying jump and link, say jump.
yeah, it's a jump and link. The IR basically supporting direct jump and link. Right.
So isn't the purpose of the tail call recursion, tail call optimization, the fact that the last thing in the return, so to speak, is a call to the current block of code?
No, the purpose is so that I can call endlessly recursively and never run out of stack.
Yes, exactly. So a call reuses the same stack frame. So the tail
After
call
you've closed
optimization is,
After you've closed the cycle. So a call jumps to something, jumps to something, 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 jumps back. I call in a big loop and I came back around to myself. If I've tail called all the way along, now I have a loop. And effectively, if I inline that whole roll until I self call, that's the loop. Is that, we're missing
right, I
that.
mean, the way I've implemented it previously is just you add one register to the frame.
Yeah.
And that's your depth count for that frame.
Right.
So it becomes a virtual, if it's 0, it's the first time. If it's 1, it's the second.
Right. So if you have a depth call on the frame, and then you end with, instead of doing a call to myself and a return, I just do a jump. That's the loop. But you want to have the depth count. Okay,
Right.
that required you to have the entire visible set of things that form that cycle available at the same compilation unit at the same time. Whereas tail call elimination says this will still work if I don't compile everything at the same time. Like I'm crossing module boundaries, I'm crossing independent compilation unit boundaries. A calls B, which came from some prior library, somebody compiled somewhere else, which calls C, again, prior library somewhere else, loops back onto A. I still don't grow my stack. That's what tail call elimination does.
Yeah, I haven't had any experience with the combination of inlining and tail call recursion. So
Well, no, it's the other way around. You've only had the experience of you inlined until it was all the same guy, and then you saw the tail call and could turn it into a loop. If
right.
you can't inline to the same guy, can you still make it work without infinite recursion? That's.
Do you plan to
it's
keep
just
around
like
any stack evidence that a tail call has occurred?
Same as
Oh, yeah.
Cameron just said.
Oh yeah, definitely. Because
the count.
otherwise you go to infinity and you can have problems.
Right. You have an infinite loop as a tail call and you don't know what happened. I don't know. There's a bunch of things where you'd like you throw an exception in the middle. And I'll just say, you called some complicated shenanigans and then it looped some number of times. Here's a sample stack frame of the last set. There were elided umpteen sets, and then you got out.
Yeah,
Like you had some prefix. Then you had something that was going to loop through a complicated shmoo, and then you went in and then you died. And I unwind to the complicated shmoo looping point and said, here's this. Oh, you looped a bunch of times. Here's the count of times you looped. I don't know what was in them. And then here's the rest.
Yeah, so part of what you lose is, the call sites of those recursions, right?
Yes.
Because they may not be all in the same place.
Yes. And
Right,
they don't
but
have
you
to
don't
take-
necessarily have to. If the thing that I have as my stack frame that says some tail recursing happened here is the set of functions that were as part of that loop, and then per function counters, I could be like, hey, you entered the state machine and you did state 1 37 times and state 2 1 billion times and state 3 exactly once.
You don't get the whole point here is because you haven't kept those frames, you don't get the exact frame contents, and you don't want them because they're too deep. There's too many of them. You ran 1 billion times, you don't have a 1 billion sized frame, you can't have any place to store that data. So you don't have them. So you
Right,
have to
but I can
approximate.
keep
What is your approximation of choice here? There's a
Mostly
bunch
what
of-
I've seen is a straight up counter, but what I would like to see is a per call site counter.
Yeah, okay, fine. Yeah. You know, if the calls are small and commonly inlined, that'll be your overhead, is counting those counts. You know, we're Ball and Loris doing the profiling data, exactly what you just asked for. I have an arbitrary graph that turned into a fixed point that came back around. And I went to profile my path through the arbitrary graph. Well, if I have the whole entire arbitrary graph in front of me, I could do a Ball and Loris optimizing profile counter game on it and do okay on those counts. And it's just profiling counts. So it gives me 5% slowdown. If I don't have them because they're all cross-called at independent compilation units, then I have way more counters than I need or want. And all this guy did was load a value as his service and return it. And the count is like 10 times the cost of loading the unchanging value. Load the stop me flag, the volatile be done now flag, and return. Okay, do atomic add 1 and load from a fixed register that's never saved, never moving, and then you're all one cache. One's 100 times more expensive than the other. So I'm not saying you should or you shouldn't. I'm just saying there'd be some kind of dragons there you just asked for. And so I also want to say thank you to whoever's doing the secretarial work. Is that you, Cole? Somebody's doing it.
I think it's all of us, but yeah.
Okay, somebody's piling in, so thank you for whoever's doing it.
What is Ball and Loris?
Oh, I feel like I got a link. This is like Matt's job. Go find that link, Matt. I'll look at Ball and Loris profiling. It's an old here, efficient path profiling FTP paper. Now, this is a really old link. Let me see if I can get a PDF on it. Here's a more recent version that's citing them. Here's people talking about it. Where's the original? Here's the paper. Here's maybe a hook to the paper. 1993. So this tells you, you know, how old I am. It's just too much here. Let me go to the bottom, throw in some Ball and Loris profiling. So that's not necessarily the right link. But when it was just like in any DAG, not cycle, in any DAG, you can look at all possible paths and minimize the set of counters you have to throw in, so you can uniquely determine the set of paths you went through. Right. So you know, if there's arbitrarily complicated shmush, but it's a DAG, and there's some minimal set of counters. That's what they went through and said, yeah, let's go profile this way. We'll get you exact path profiles with minimal counts. And then,
And is SSA always a DAG?
no, of course, I
Yeah, I
directly
didn't think
represent
so.
loops.
Yeah.
And in fact, when I build SSA, I do not build a minimal SSA because it's not worth the trouble. I build cheap ass sleazy quick SSA, and then I do the obvious people optimizations to clean it out, and I get a pretty damn close to minimal, good enough SSA form, but it's definitely got cycles in it. Somebody asked for building SSA from Java bytecodes on Twitter, and I intended to go do a doodle on it, and I never got around to it because it's a bunch of work.
You could just send them to the OpenJDK link.
Just do what?
Send them to the hotspot link.
Oh,
on
yeah.
OpenJDK.
Well, go read this giant pile of code that's got 25 years of accretion on it. It's hard to read. The core concept's still there, and it still makes fast, good SSA form. But there's a lot of crap floating around it now. It makes it hard to read. I've been there on that front on a number of other people's. Hey, bye. Other people's.
Yeah, we don't do it this way, but like a nice way to do it would be to just, if you use LLVM, emit loads and stores to the like to the alloca, which represents your local state, like your locals, your stack, and then just run the standard pass, which does promotion from alloca to SSH. Basically, yeah, basically the same way like Clang does it. We don't do that. I think we just didn't realize that we could do it straight away. We do manual construction, but that's a cute trick, I think.
The C2 does basically that, except he does the promotion on the spot as you build. Like you throw a load in, he promotes immediately.
Yeah, that's what we do too.
Okay. And then at loops, I put down a conservative set of fees for every possible Java variable that might come back around. And I just leave it hanging as fees that can't be thrown away yet. And then when I do fold them in, I run through immediately and look at all the fees that merge the same thing twice and get rid of them at that time.
One trade-off with that is that it kind of kills debugging performance. I don't think before SSA-based compilers, we used to do the memory allocation for everything. So debugging performance for C and C++. Debugging performance for C and C++, which means 0, which means those load and stores are not eliminated, which means it's very, very slow. For debug builds.
Like in hotspot, you flip back to the interpreter. You're running in JITted code, doing whatever the hell the JITted code does, and then somebody says put a breakpoint in, and you stop at the next safe point, which you don't get to pick. But whenever you hit insert maybe now breakpoint, you stop at a safe point, and then you're back in the interpreter, which is doing it very slowly. Yeah, step by step.
Right. I don't think that was the trade-off before the SSA-based compilers. I'm thinking really, really old compilers like Borland compilers. I think they had reasonable good debugging performance, but they also didn't use SSA in their construction.
Right. Yeah.
That was an interesting
but it means that I think it's just a question of how much did they do in 0 compared to like other optimizations.
Well, you had to, okay.
Right, exactly.
You had to keep enough state that as you marched 0 forward, it didn't lose the debugging property. Your dwarf could find the data.
And I would argue that I don't think that's the effect of SSA representation. I think it's just a better separation of optimizations, and that you can just easily switch things off and still have something functional.
Yeah.
It's also an interesting choice would be to run only Mentourage. So like 0, I think it was actually recently committed to LLVM, that there is an option that basically run 0 plus Mentourage. And that can actually be not a bad trade-off for debugging. I'm also thinking debugging these compilations when you have to read LLVM IR. It's still actually more readable when you let Mentourage pass run on it once.
Mm-hmm. Yeah, certainly the sort of C2 philosophy is you kept the architected state around, except in C2, you just threw it away, except at once per loop and once per function call. But if I wanted it once per line, I could give you the architected state per line and optimize between lines, and that would let you single step forward and still get the entire JVM state.
No, but you keep this state like basically on a side table as you parse. The idea with explicitly emit loads and stores, you basically just emit the code which produces this state, and then you let other optimizations clean it up and produce nice SSA.
That's what C2 does. Yeah.
The only difference, it maintains the state on the side. It's never explicitly in the IR as a buffer where you like put things on the stack or load things from the stack.
You're talking about what C2 does?
Yeah. Well, it's not what it does. It has the state on the side.
C2 pushes the state in the IR directly every time.
Well, do you mean that there is a buffer in the IR which IR manipulates, where there are loads and stores from that buffer which are later converted into SSA?
So there is a load or a store-like thing done that is immediately optimized into a mem-to-reg-like behavior such that you don't actually see the load of the store. There is also the loader and store lifting as an optimization, but the parser knows it's going to happen and eagerly does it inline on the spot.
Yeah, that's well, essentially that's what any any compiler would need to do, and that's what I mean, that you maintain the state on the side. Like you have some site structure where you know the VM state, where you know the locals, where you know the stacks, and then you do this kind of lifting to SSA on the spot, knowing the site table.
Okay, and then, you know, when I say lifting to SSA, the nodes are directly in SSA as they get produced in the first place. There was no, I'm not SSA, now I am. They are in SSA from step one, from whole cloth, from creation.
Yep.
Okay. I'm hearing side table a lot, and you know, there's side tables to hold things like the depth of the stack was not actually kept as a counter in the IR directly. So that is in a side table.
You still need to maintain the, okay, maybe I misunderstand something. You need to maintain the state, meaning the locals and the stack at any point as you parse.
Yes, that's called a safe point node. The parser has a dedicated safe point node that it's stepping forward as it parses bytecodes.
So do you emit this as a node at every bytecode?
Safe point node is the moving forward cursor. I emit the semantic IR pieces for the bytecode I'm parsing as a mutation to the existing safe point node.
Okay,
as a mutation, that's not the right answer. Wait, I make a new node, like I come across a field load. I make a new node, which is the field load, and the safe point, which has a representation of Java registers and Java stack, puts the appropriate pointer to that node. And that node points to where it gets its address from and its memory state from.
Okay, so that's what I meant as a side table, but it sounds like you have this expressed as a node in IR, and every instruction points to the node corresponding to the state.
Yes, so it's one node, and then when I parse the next bytecode, the same safe point node picks up the new state. So it's continuously mutated as it rolls forward. If I hit a point where I need a safe point, because it's a GC backend, or it's a GC, it's a call to whatever, that's the safe point that gets used, and I fork a new one off and I go again. And that guy just gets left behind.
If you squint, you can say that this updated node is a side table which maintains the state.
You could squint at it, yeah. That way, sure. Like I said, I leave it in the IR from time to time because it represents, like I come to a loop head, I need to merge from back edges, I don't have them yet. There's a safe point there, which is mapping to the current state of the fees that represent the possible back edges. And then I have a new safe point that starts picking up mutations going forward. And when I roll around, I have merged these two safe points. One of them is known to be pointing at a bunch of fees, and one of them's got a bunch of edges, and they just pile one per each fee.
And that's not a meaningful distinction in your IR, because your IR is a sea of nodes, not a document.
Right. But in my head, it's a sea of nodes. It's all just nodes in a graph. And then as soon as they're, right. So you could claim, or you could think about the safe point as it's rolling forward as it's effectively kind of a side table. It's the cursor representing the machine architected state that's rolling forward. It's the cursor into the bytecodes and pointing to the machine architected IR that's getting rolled off the end of it. Like a loom weaving cloth, endlessly the cloth rolls away from the loom, and you're adding new pieces to the cloth as it rolls away from the moving loom point.
Oh, a question. So I can see how you can maintain this state as you parse. So for every bytecode, you model the effect of the bytecode on the state. And you have access to the state at any point you want. But if later during optimizations, you want to reconstruct a state at some particular point,
right?
Do you have access with that? Or do you have access, do you know the state for points where you didn't explicitly emit a snapshot of the state?
No. I explicitly emit a point where I want to track a point during parse. I explicitly emit a safe point. So the parser emits eagerly extra safe points where it can't tell that it's going to need one. Like I have to have one for every loop because that's your safe point to stop the loop. So if I don't have one in a loop, the loop can't be interrupted for GC or cal oscillating or anything. Fine. So every time there's a possibility of back edge, a safe point gets put in, even if that package later is optimized away. And then there's optimizations that simply look at safe points and say, I have too many, I can get rid of some of the extras. Because it's just another node in the graph, another peephole says, yeah, I got one in the loop, I got another one in the loop, okay, one of them goes away.
So Graal has an interesting trick where they remember the VM state at side effecting operations. And thus they can basically for any point in the IR, they can look at the dominating side effecting operation and take the state after that operation. And this would be the valid state you can roll back into interpreter.
So for me, the valid state is what got fed into a safe point. Semantically, a safe point is a call that is taken with very low frequency that carries the entire architected machine state, and it is intended to call into the interpreter and have the interpreter carry forward, but it could GC or whatever hell you want. But it has all possible machine architected state, and it returns completely updated machine architected state. So a debugger can come in at a safe point and change all the local Java variables and carry forward again.
Yeah, but then there is no guarantee that at any point in the IR, you would have some state available.
That is correct. And also, no one cares. All I needed is to stop it at some point. So you want to stop at this point here in a hot loop. The loop's currently running. There's a safe point somewhere in the loop. You want to stop here. What do? We stop it at a safe point on one of a billion iterations. And you can't tell which iteration you're going to get when you stop it. So you stopped at one point. Then I roll forward in the interpreter to where you said I set my breakpoint.
Oh, the reason I want to have a state available at any point is if I want to do some optimization, which let's say I want to insert a deoptimization late in the optimizer, not early in the parser, but somehow I figured, oh, it would be nice to deoptimize here. And I'm like, do I know the state to deoptimize? And maybe I do because there is a safe point nearby and there haven't been a side effecting operation between safe point and my point. Or maybe there is no safe points with valid state, and I cannot do this transform.
That's correct, and that's what I do. And I end up de-optimizing wherever I want anyhow because it's not hard. Sometimes if you're running through static straight line code, I don't need to optimize here versus there. The deopt doesn't make any sense there. If I have branches off to things that I've chopped off or said this might happen, and if it does, I have to undo or redo ops, those places all have their own safe points. If I'm in a hot loop and I want to do something where I want to come up with some point and then say, I need a deopt here, I peel the loop and I run some section without any of the fun stuff. And then I get to wherever I want to be in the body of the loop and I can break out with the valid state and I'm done.
Oh, you're saying that, like one of the examples where I want to have a state, but I don't have a state is, let's say I want to sync allocation down to some cold path. Because allocation is a safe point also, I need to have a VM state for possible deoptimization. That's how it is in hotspot. It doesn't have to be this way again. But I need, in order to sync the allocation into this cold branch, I need to know the VM state at that cold branch. So if a deopt occurs at that allocation, that new allocation side, I know how to
allocations are a deopt point.
Yeah, but
all allocations are a deopt point.
This is an example of an optimization which needs a deopt state at an arbitrary point, or at least at the point where I want to sync the allocation to.
Yeah.
And if I don't have the state available, I cannot do this transform.
Okay, so you have the state because all allocations have that state.
Wait, but it's a state at the original allocation site. Let's say I have an allocation, then I have a side effecting operation, a store.
Yeah.
And then I have a branch. And I want to sync the allocation down to cold side of this branch, but there was a side effecting operation, so I cannot reuse the state from that allocation.
Yeah, I got you. I got you now. So I don't do that. If I have a side effecting operation, the allocation won't sync past it. Like there are a set of narrow optimizations that move side effects across safe point boundaries, but typically no, because if you take the jump off to the interpreter, you have to do the right thing. So you have to manually step the interpreter state across the deopt point, if you will, or across the safe point, if you will. So I simply don't do that. Instead, if I want to shuffle the order of a side effect and an allocation, I'll simply clone the code and push it down the off path with the with the side effect there and the side effect over here. I'll move the test that breaks off earlier versus whatever. There's
That's the way to do it.
obviously things you can do to maintain semantic equivalence that moves a constant amount of work off on various branches. And that's
but now if we go back to that, to the way Graal does it, they have the state associated with side effecting operation.
right.
So when they can sync the allocation past the side effecting operation, then take the state from that side effecting operation and deopt to that state if they need to deopt at that allocation.
Right. So I voted to not carry the deopt state, the machine architected state, with every side effecting operation, because there's too many of them. Whereas the number of places where I do carry the safe points is actually, it's like calls, it's new operations, it's all the fail out places if you blow a range check or check cast or whatever, and nothing else. And that turned out to be just totally fine in terms of performance optimizations. Occasionally you'd have a thing where you said, I have a new and a side effect, and I want to swap them, but if I swap them and then the new fails, I've taken the side effect, but the new doesn't have the notion that you shouldn't have side effected or not. It's in the wrong place. And I simply said, oh, I don't swap these two unless I can prove there's something going on there that is correct, and I don't care. Like occasionally there's a you're no alias and the side effect can happen either order, and I don't really care. But usually the answer is I can't swap them. But instead, the reason I'm deopting is because the safe point itself, the new itself has a fast and a slow. The fast path is, the compiler knows about it, and inline's the little fucking diamond, and the diamond is do a test, it rarely fails, here's what happens if you fail. Now I have a diamond, and I have a side effect. I can push the side effect down both sides of the diamond. On this side of the diamond, it can carry through and keep going. On this side of the diamond, it's pinned by the new, but then it can't fold back in if I drop the safe point down below. So there's still a graph optimization that you can carry on through there that says, if I'm going to diamond on a new and I'm going to come back into the same code, I don't really care if the side effect is before or after, because it's not going to change my performance. If I'm going to diamond and I really badly think that if I never coming back because I want to do something else over here, like it's a rare off path that never returns, like a fail mode, then those get chopped off to the interpreter and they become not a diamond, but a T, and you will go away and never come back. And now I can reorder helter skelter.
Well, we do what we do with deopt states is what basically C2 does. So we don't have the invariant that at any point we have the VM state available. But there are optimizations where we would like to have this. And yeah, you're right. There are different ways we can like work around this by cloning the code. But still, there are sometimes cases where you wish you have it.
You know, I got over that. I'm not saying it's not true. It was. But the cost of that state maintenance for the straight line code that didn't use it was actually fairly substantial. There's a lot of shit it demands for the machine state of the interpreter that you go to that the JITted code doesn't care for. And so it was more important to minimize the number of deopt points that you had around than it was to track extra points so I could choose to deopt at other places. I had no problem teeing off to death zones if a heroic optimization was going to fail that had some point where I cloned you off to, and then on the not fail path, oh boy, you went hog wild. You know, everything got reordered to heart's content and away you went. So like networking byte buffer, direct byte buffer code would grab 4 bytes at a time from a 4-byte packet buffer and unwind them and reorder them and shuffle. And you had these 4 bytes, array of 0, 1, 2, 3. So the array of 0 was tested first, an array of length of 1, the array length of 2. No, I moved the array length of 3 check up front. So it could fail if you passed in an array length of 2, and it would do 0 and 1, and it should have blown at 2. And instead it would blow as if 3 was blown, but it blew, you know, earlier. And then you just ran it in the interpreter, and suddenly you got rid of all the range checks, or 3 out of 4 range checks went away. And, you know, the length 3 hit some of the other check that happened earlier. I remember cleaning out network code left and right. There's a lot of these things where you could just shuffle the tests around pretty eagerly. Once you didn't have too many deopt points, because those are always where the choke point was for scheduling and optimization, was the deopt point.
Yeah, and you can argue that having these deopt points can inhibit some other optimizations because they just capture more state from the compiled code.
Right, that's what I'm arguing. They routinely did, and so I didn't want to have as many. Upon rare occasion, I realized I took a deopt at an unfortunate place, and had I captured the deopt state at a different location, it would have been a better deal. And usually that was sorted by some amount of loop peeling to bring around the safe point to where I wanted it in the iteration on the loop.
Still seems like a lot of save points though. Every call, every new, every time you go back to the top of a loop.
Right. So the new allocation save points. So break out the ones you had to throw in because you had to allow an optimization. You had to allow a deopt at any point in time within a reasonable time boundary. So the rule was a save point every 1,000 clock cycles or so, something like that. So those were once per loop, once per call, except you inline, and so the inlines cleaned out, and you had to once per after inlining call. So that was your recursive case, had to have one per call. And in fact, it's usually tail recursive. Like the call itself, the other guy made that a safe point. But you're in a call, when you tail call to somebody else, the tail path would return as an infinite unwind, and you had to have one there. So you ended up with one per call, one per loop. That was the rule. Plus, you needed one for every time you're going to stop for any other reason that you might have to figure your state out. So the obvious fail modes are any of the exception throws. I took a null pointer, I took a range check, I took a check cast. Those are the 99% cases. They immediately threw some horrible stack frame. Occasionally you had a case where you're going to catch it, do something clever in the compiler. That was a lot of work, but the 99 cost case there was, I had to support, I'm throwing a range check exception, fucking give me the index at blue, right? And the array length and all that shit. So that was all required managed state. And you teed them off to the interpreter, but they had to be live to go to the interpreter. Then you had news. News were always in hot loops. And in the hot loop, the main path would never ever stop for the save point there because the new never failed except when it did. When it did, you didn't need a deopt. Typically, you needed to just do a garbage collection. Except that now that you're stopped, classes got loaded and you did in fact needed a deopt. So that was the most expensive one, was basically the required one, and then if you did a new, the required on the new. And you put the new, like I said, you put the diamond to expose the compiler, and the new got off to the side, and you sunk side effects into the off path, and you did cleanup on the return out. Like you had an induction variable that you turned to a point of stepping through, right? You had an induction variable. If you did a GC allocation, the induction variable was wrong on the off path coming out, but you could rebuild the induction variable on the off path on the return from the GC, and then tee back in and have your induction variable go again. So, you did what you could, but yeah, there was some cost there. And in fact, in practice, if you look at the performance of Java, eventually it got acceptable. A lot of it was I had to compute some value for the interpreter that the JIT didn't need. And then all I had to do was store it somewhere. And x86 would eat a store at no cost, not quite zero, but damn fucking close to zero cost. So register math to compute, store it in memory. It's dead as far as I'm concerned, but the cost to compute was a clock maybe, and that, so it wasn't too bad to compute the state periodically. You just didn't want to do it too often.
And you're not reading back those stores, so it can just go into some store buffer. And
right, I read them back only if you took
the CPU will get around to writing that at some point.
Yeah, if you took the def path, you stopped and read the value. Yeah. The other thing, of course, is if the loop was really tight and you had a save point in it, then you wanted to unroll. And so the cost of a save point was divided by the number of unroll factors you put in. So you just unroll the loop enough, and then the cost would dwindle down to, you don't care no more.
Yeah, and I guess the fact that a GC save point and a deopt point have to be the same thing, it doesn't have to be this way. It's just a quirk of hotspot. And
right.
For example,
and we've fought back and forth for a long time at hotspot, and so far the answer has been there's not a terribly demanding use case which is improved by not having it.
Well, for example, that optimization was syncing the allocation.
Yeah.
If we eliminate the deopt point at an allocation and leave it just a GC save point, now we can move allocations freely because there is no need to capture the VM state for the allocation.
Right. In my experience, moving allocations hasn't been a giant payoff. Getting rid of allocations, big payoff. Moving them around, not a big payoff.
Yeah, that's I think the only remaining gap between what graal escape analysis does and what we can do. Like we can eliminate in all cases where they can eliminate, but they also have syncing. We don't, because of this issue with the states tracking. And I don't know how much how much gains we're leaving on the table here.
Right. I sorted on this a long time, and in fact, I sorted at C2 Azul a fair amount. Like, what are I do with allocations? Can I sync them? Can I relift them? Kind of combine multiple allocations so one test covers the entire allocation set for the trip through the loop and that kind of stuff. I didn't see a lot of performance gains. There were a lot of funny issues, so at some point I left them off the table. Yeah.
You would think combining allocations would be valuable, considering in like actual user code at the top level, combining your allocations is often a huge win.
Yeah. Well, that one I think is because you get rid of the indirections that you have, because you've got a string header pointer, string character array, and you chain along, and you can squish them. You get rid of the linked list indirection. I wouldn't get rid of the linked list indirection. I just have one save point and one out of memory test. The out of memory test is super cheap, and the one save point is, since I have one, I have 2, 3, and 4. They all have deltas from the 1. Well, the deltas are pretty cheap too. So the 1 cost me. The 2, 3, and 4 were not so much more extra cost.
So when you are saying combining allocations, basically you are combining the TLAB top check. Instead of doing it for every allocation, you do it once for the total sum of their size.
Yeah,
and that's the same.
Basically, check the T-lab for the Deopt. Oh, it didn't fail. I'll then bump a pointer that just as I allocated, because you did different paths and you took different allocations. You did a max test for the body of the loop, and then you bump a pointer as you used on the whatever paths, and then you had some leftover that you didn't use in the max case. You just handed back to the T-lab and used it for the next go around. That was the theory that I was working under, and then I would not have so many tests, not have so many Deopts, and my more limited testing said I wasn't going to gain much, and I had other things to go do. So
we do that. It is like enabled optimization, but yeah, it doesn't give that much, like maybe a few percent here and there.
Yeah. Whereas what you talk about, Aaron, was object inlining. I think that would have a lot, because that says not once per allocation, but once per use of the structure, I skipped a linked list indirect. I think that's way more useful. Well, here we are at 11:45. Anyone else want to pile in with something?
It's been a long week.
I may have missed it. Did you give the AA update at the beginning?
I didn't. Not a whole lot to say. I've been steadily making progress. I'm slowly turning back on all tests with the new combined algorithm running. I'm sorting out all kinds of funny typing issues that I've in hindsight seem obvious. It's like all these things, like I've been at this like 2 years, 1 year for Henley Milner, no, almost a year, 3/4 of a year. And in hindsight, there's a lot of things like, oh, of course that's obvious. And going forward, it was not obvious. I could have, should have done differently. So I had to replumb a bunch of low-level shit to get the right facts pulled through. Then it turns out that like the main issue I'm stumbling right now is I don't have any first types for the data flow for external callers. From within data flow math, doing data flow, calling data flow in all directions, building a call graph, I have everything perfectly done. It's all great. If you have an external module entry point, I can't tell you what type you're allowed to send me that's what Henley Milner does.
By external module, you mean FFI?
I make a module and I export an interface to it, an ABI. Okay, what is the requirements of the caller who's going to call this module? What's he going to send me? So the forward flow thing says, I don't know what he's going to send me. He sends me the worst case possible scalar value. All right, immediately I throw type errors left and right. I will not work if you hand me an int where I need a pointer to a person or vice versa. So Henley Milner would come back through and say, this has to be a person pointer. And I have to turn that around and say, oh, the flow side is only going to take a person pointer here. So the turnaround point becomes a place where I don't have I provably don't have a most, what do you call it, most principal type. I can hand you scenarios where you could type it one way and you could type it another. And some of those things look really stupid. Like, why would you ever go here? But the math just works out that way and allows it. So I had to go sort out how to deal with that. Now we can go, I'm happy to go down here because this is what I've been wrestling for the past 2 months. But this is like not a short conversation and it's already noon or heading toward noon. So there's a thing there. And then hand in hand with this came this notion of, if I have an external module entry point, do I really want to infer the types? Or do I want to say for an external module entry where you're expecting separate compilation and another user is going to call you, you just be explicit and name the types. You are required to name types here.
I mean, if I'm just going to name them, I also want, like, I kind of want strong assertions on the types of the borders.
No, I'll give you total type safety in all conditions. You will never be allowed to run code that is type unsafe. Okay, but if I have a module where you've inferred, like I give you a module and all the module does is return time value as an integer, returns a long, takes no arguments, returns a long. Okay, I'm going to infer it takes no arguments and it returns a long, and you don't have to put anything on the annotation. You have an external sys.time and it says it takes no arguments, and the actual code for the time guy doesn't have any type annotations because I've inferred it. Oh, that's great. Is that what you really want? Okay, here's a type annotation for something that I don't know what the hell. It does a range check on 2 time things. I don't know what. It has some things it takes as inputs. Here's rand. It takes an integer input and returns me a number from 0 to n-1. I'm going to type infer it. Okay, you go look at the code for implementing rand. It has no types on the calling argument. What's this argument x that's coming in? Well, that's the range of the random number generator. So maybe you want to give it a better name. You know, internally in your own code, type inference is great. For some sort of crossing boundary point, you want to say, this is the long. This is a long here. You're handing me a long value, or a int 64 or whatever. You're handing me something, right? And that's the part of the annotation for the module. So I can infer those, but I think I want you to name them. Well, if I make you name them, that fixes my forward flow problem too. So this is what I've been wrestling with for like, why does this suck all the time? Well, after I got the principal type figured out that you didn't have a principal type, that was really obnoxious and hard to discover. As soon as that one figures out, then you can come through, okay, what can I do about it? And then there's some obvious things to go do. And then the second obvious thing after that is, well, you know, if you gave me a type in the first place, that was your principal type. I'll go verify that it works.
Being explicit at the boundaries is not a bad thing.
That's what I'm totally there. And
yeah, the one place that I think of that can get
support.
painful is if my library is depending upon another library.
Yeah.
And like I'm calling this function and it's going to give me back a thing of some type.
Yeah.
And I'm basically just flowing it through me.
Right.
And then I'm spitting it out the other end.
Right.
Sometimes what I want to say is, hey, this thing that I spit out the other end is kind of whatever my dependency gave me.
Yeah.
And if I have to name it, suddenly I have to import a name from that package for that.
No, that's just a name type parameter. I mean, that's
you can have polymorphic types there. That's okay. I'm handed a thing of type T. I pass a T off to X. X hands me back a T prime, which is related to T somehow. I hand a T prime off. That's okay. You started out by saying, I got a T. And that's all I need to know.
Okay. So even if it's just the type that I'm passing out is whatever type I got passed in on this other side.
Right. Yeah, this is a polymorphic thing, so that's okay. I got nothing. Right now I have nothing coming in, like by default. Like I allow you to write this code that says, here's a top level function you're allowed to call. There are no parameters on the arguments. What do I get? Well, Hindley-Milner will say, they need to be the following things. And the flow typing says, I get what I get. What are you handing me? And he'll pass it forwards perfectly. It's a forwards flow typing. But he starts from somewhere. And the start answer was, can I handle a scalar? No. Oh, he errored out immediately.
The other reason is if you ever do get to bidirectional type inference,
that's Hindley-Milner. Yeah.
What'll happen is you'll have an error in the calling code. But if you don't hard type the boundaries, that error can flow through the module that is already known to be correct,
right,
and show up in the wrong place.
Right. What will happen here is you've called from your guy and said, I have type X, and I call out to some other function, and he says, this X and this Y are incompatible, and you want to blow over there. And we're actually working really hard, Cameron, to get that message back over here.
Right.
So this guy says that guy is going to blow up with X is not a Y if I pass an X in.
Just do it the C++ way of the C front way of doing the error composition. You just pick a random number that's 15,000 or greater, and then concatenate that many random ASCII characters together, and then put the name of the method at the front.
Yes, yes. Error number 15765 : does not compute. Chuck, you very much.
I definitely vote for strong typing at your boundaries. Yeah.
All right. Well, heard. I've been trying to get like type inference working everywhere. Well, the answer is actually I don't want it to work at the boundaries, and it's really hard to do it at the boundaries. Maybe there's a clue here.
It's also a good place to avoid super linear things from happening.
Well, there's a different thing that says I want my typing system to run in a reasonable X time as well. You know, it has to.
So Facebook ran into problems like that with their type flow system.
Oh, okay. Yeah, I can play that. Yeah, type flow.
They're trying to type flow through a lot of JavaScript.
Yes, right. Yeah.
And some of these libraries are really big and it takes a long time.
Yes, right.
And they realized that they had to start adding explicit type annotations at the boundaries of all their modules. And suddenly the runtime went from
because they weren't actually
order the size of the code base to order the size of each of your modules.
Yeah. I'm hoping I can keep incrementally computed types as part of the IR everywhere, so that when you do a linking step, that it's only the interface size that has to be computed, not the size of each of the independent modules. So I am in a zone where I have all the incremental types everywhere, and you know, knock on plexiglass or whatever the hell I'm looking at here. We'll get there.
Yeah, that's really appreciated. I want to be able to change one character in my file and get the type inference to re-happen with less time than it takes to run the entire code base through my CPU once.
Without running you, yes. Right, exactly. All right, folks. It's excellent. And like I said, if anyone wants to talk type theory with me about this kind of shit, I'll have to go really deep, really fast. But not today, or not on this coffee club.
Put it on a to-do for next week.
Yeah, we'll reach out too if you want to do. I don't know if everyone else is excited. Maybe more excited. I can't tell if it's going to drive everyone in the hole in the ground. And of course, I don't have any visual aid docs to help speed it along or make it publicly available. Like if you don't know what Henley Milner does or how it works, maybe you're not getting so much other conversation, and that's not helpful. So there's something to be done there. All right, till we meet again.
Cool.
Bye.
Cheers.
Bye.